welcome all the participants to this online session dedicated to semester 4 Electrical and Electronics Engineering students. The subject for the session is synchronous and induction machines, and the topic will be single phase induction motor. It is a continuation of the previous lecture. Today's class instructor will be Ms. Anita Matthew, who is working as an assistant professor at IES College of Engineering, Thrissur. She has more than 7 years of teaching experience. She did her graduation in Electrical and Electronics Engineering and MTech in Power Electronics and Drives. On behalf of ASAP and ASDC division, I welcome you, ma'am, to deliver today's class. And on this note, I would like to welcome all the attendees to the session. Let me conclude this introductory part by giving the outline of today's class. The entire 1 hour class will be divided into 2 continuous sessions, and each session will have 20 minutes of lecture and 10 minutes of question and answer interaction. And during the interaction time, students may use the question and answer window or chat window to post their questions. All the students are requested to maintain a classroom decorum throughout the session. Anita ma'am will be available online throughout the entire 1 hour session. Ma'am, you may please start the session.
Okay, thank you, Ashish. Good afternoon, all. I am Matthew, Assistant Professor of IES College of Engineering, Chittilappalli, Thrissur. Last session, we were dealing with the module 6.6 itself of synchronous and induction machine. Some of the topics were covered in that session. Rest of the topics will be covered in this session. See here, this is the syllabus of modules: induction generator and induction generator and synchronous induction motor were covered in the last session. In today's session, we will be covering single phase induction motor. In single phase induction motor, double revolving theory, torque slip curve, equivalent circuit and types are mentioned in. All these topics will be discussed in this session. Okay, before going to this single phase induction motor, I would like to explain some basic concepts of three-phase induction motor. I have already explained it in the last session. Okay. This is the construction of three-phase induction motor. You can see here the mainly 2 parts. This stator part and this is the rotor part. Okay. In the stator part, there are slots in the outer periphery. You can see slot. 3-phase windings are placed. You can see the windings. These are the windings. Okay. These are the parts of stator and rotor. In the rotor core, the outer periphery is slot, and inside the slots there are copper or aluminum bars or winding. It depends upon the rotor type. In squirrel cage rotor, it is aluminum or copper bar, and in slip ring rotor type, the winding slots are provided with windings. Okay, this is the construction of induction motor. The basic working principle is Faraday's laws of electromagnetic induction. When we are applying a 3-phase supply to this stator through the terminal box, what will happen? A rotating magnetic field will be developed here, and this rotating magnetic field cuts the rotor conductor, the induced current. Okay, thus a torque is developed in the rotor, thus the rotor rotates. Working principle of 3-phase induction motor. Okay, then we are moving to the single phase induction motor. Single phase induction motor. Single phase motors are usually used for application which require capacity less than 0.5 kilowatt. There are some construction is simple, it is reliable, and maintenance is easy and low cost. These are the merits of single phase induction motor. Coming to the demerits, compared to the three phase induction motor, overload capacity, efficiency, output, power factor, all are low compared to this three phase. Okay, these are all are the demerits. Then coming to the construction, here also there is a rotor and a stator, as in the three phase induction motor. Rotor of three phase squirrel induction motor. In the stator, here also there are windings, but they are single phase winding instead of three phase winding. Okay, in three phase induction motor, it was a three phase winding, either a three phase winding. In squirrel gauge induction motor, it was a three phase winding, but here we are using single phase winding. And another part is main winding and auxiliary windings. That means here, a part of the main winding, part of the stator winding, there are some auxiliary or starting windings also. Next is the centrifugal switch. There's a switch. It is used to cut out the auxiliary winding after starting. During the starting only, we need the it is not needed. So the centrifugal switch is used to cut out it from the circuit. Okay. Simplified figure of the single phase induction motor. This is the stator winding, this is the rotor, and here supplying a single phase supply. When a single phase supply is given, single phase supply is given, what will happen? A pulsating magnetic field is developed. That is, a single phase current flows through the stator circuit, a pulsating magnetic field is developed. This pulsating magnetic field will not produce any torque so that the rotor could rotate. So the rotor cannot rotate. So that's why single phase induction motor not self-starting. Okay, in three phase induction motor, instead of this pulsating magnetic field, there was rotating magnetic field. The rotating magnetic field cut the rotor conductors, and the rotor conductors induced EMF is produced in the rotor conductors and induced current. Okay, that's how in that case. But here, no rotating magnet. Okay, the pulsating magnetic field, mathematically it can be two components. Okay, two components means two of equal magnitude and opposite direction. So these two can get cancelled and net torque will be 0. Okay, this theory is known as double field revolving theory. Okay. This is the double field revolving theory. You can see here. This is the, you can see, this is the state flux. That is the pulsating flux with the amplitude 1m. Amplitude means the maximum value of the waveform. Okay, phi 1m. This pulsating field is resolved into two fields. Both are having same magnitude. The magnitude will be phi 1m by 2. You can see here phi 1m by 2. Magnitude, these fluxes will rotate in opposite direction. You see phi f is rotating in this direction and phi b is rotating in this direction. Both of them rotates in opposite direction. Okay, One flux is phi F, that is forward flux, and other phi B, that is backward flux. This is another representation you can see here. This is same as that we have explained. Phi F and phi B opposite is opposite direction, and in one instant and in another instant are in same same position. This is shown in this figure. Okay. Next. Still, at standstill means the rotor is not rotating. Standstill n equal to 0. N equal to 0 means the rotor speed n equal to 0. When n equal to 0, slip is equal to 1. Why is equal to 1 when n equal to 0? We know that slip s equal to ns minus n by ns. When ns equal to 0, what will be the answer? What will be the value for ns by ns? Ns by ns equal to 1. Okay. Thus, n equal to 0. When n equal to 0, s equal to 1. There, two magnetic field will rotate in opposite direction. Okay. And the net torque will be 0. When it is in running condition, that means if we make any external means to run the rotor, the slips will be different for rotating field and backward rotating field. Forward rotating field, the slip will be, as the equation is ns minus n by ns, that is equal to s. Speed ns minus this is in the backward direction. So we are putting a minus here. So ns minus minus n by ns, and by solving it, we will get 2 minus s. So the slip is different different for the forward rotating, backward rotating field while running. Normal operation, that means during running operation, 2 minus s, that is minus s. 2 minus s is very greater than slip s, that is backward. At first time at standstill, the slip was 1 for backward rotating field. When it is in running condition, for backward rotating field, the 2 minus s, it is very much greater than the slip when it was in a standstill condition. What will happen? A larger current, rotor currents will flow in the by the backward field, but the forward field, less current is produced or induced. Okay. After the rotor is rotated, the backward field gets weakened and the forward field gets strengthened. Thus, the rotor will continue to rotate in the forward direction. We are providing an external mean to rotor in the forward direction. So after running, that is after starting, after attaining some 75% of the speed, what will happen? The get and the forward field get strengthened. This is the torque of the single phase induction motor. You can see here. So are two dotted lines. There are two dotted lines, this one and this one. Two dotted lines represents the torque developed by forward and backward field. The upper dotted line represents torque developed by forward field, and the lower dotted line torque by backward field. This Okay, this is the net torque developed. You can see here, this is the net torque developed at S equal to 1. S equal to 1 means at standstill condition. Okay, at standstill condition S equal to 1, that you can see the net torque is 0. That's why this machine is starting. We have the torque at the starting time is 0. Okay, so the machine is not self-starting, and you can see the overall torque will be get cancelled. There will not be any torque in the okay. Okay, this is the equivalent circuit. This is as that of the series induction motor. You can see here this R1 is the stator, X1 is the resistance of the rotor, X1 is the reactance of the stator. X1 is the leakage reactance of the stator winding. Xm is the total magnetizing reactance, and R2 dash is the resistance of the rotor referred to stator. This X2 dash is the leakage reactance of the rotor referred to stator. In induction motor, by this into you can see here the first part and second part is the first part is the is due to the EMF. You can see here EMF. EMF is the induced EMF by the forward magnetic field. Here EMB is the induced EMF by the backward magnetic field. Okay, this whole section is splitted into two, here and here, this and this, and circuit at standstill. Okay, you can see the circuit at normal operation. Normal operation, we the slip. So you can see here R2 dash by 2s, and for the forward field and for the backward field R2 dash by 2 into 2 minus s, because we have already derived that slide. In this slide you have already seen that SB 2 minus s during running condition. Okay, so this 2 minus s is considered while we are while drawing the equivalent circuit. You can see this is the equivalent circuit under normal operation. Okay, next figure is the approximate operation. Normal operation. Here you can see the only difference is that Rm by 2 is Rm by 2 from both the removed, because we are considering, because here. Okay, so we are approximating it as this. These are the equivalent circuit of the single phase induction motor. Okay, next is the types of single phase induction motor. We already discussed that single phase induction motor are not self-starting. So in order to make it a self-starting machine, or in order to start the machine, we have to go for some other means. So according to that, we are classified the induction motor into 5 types. First one is split phase induction motor, or it is also known as resistance start single phase induction motor. Second one is capacitor start induction motor. Third is capacitor start and capacitor run induction motor. Fourth is permanent capacitor single phase induction motor. Fifth is shaded pole induction motor. Okay, there are 5 types of single phase induction motor. Okay, according to the starting methods, it is classified. Okay, shall we move to the types in details? Okay, first one is split phase induction motor. The first split phase induction motor, here you can see the figure. In the split phase induction motor, a starting winding is provided, a part of this main winding. Okay, a starting winding is provided a part of this main winding, and a centrifugal switch is also there. The peculiarity of this starting winding is that this winding have high resistance. That is, you can see the detailed figure here. Here you can see this is the rotor part. This is the main winding. This is the main winding. This is the starting winding or auxiliary winding. This auxiliary winding is connected with a resistance in series, and a centrifugal switch is there. Okay. That means the auxiliary winding is made highly resistive. When the auxiliary winding is resistive, when we are giving a single phase supply, what will happen? A current flows through this winding, but how the voltage and current will be related? We know that for a purely resistive circuit, the voltage and current is in phase. But for a purely inductive resistance, the voltage and current, current lags the voltage by 90 degree. Okay, here this circuit is purely resistive. This circuit is purely resistive. Sorry, not purely resistive. This is highly resistive. Okay, so the phasor diagram, I'll show the phasor diagram. Okay, you can see that the phasor diagram. This is the voltage V which is applying, and this is the current IS of the starting current. That is the current through the starting winding. IS is the current through the starting winding. This starting current lags the voltage by a small angle phi s. If it was a purely resistive circuit, the current IS and voltage would be in phase. Okay, if it was a purely resistive circuit. But here it is not a purely resistive circuit, but it is a highly resistive circuit. So the voltage, the current lags the voltage by an angle phi s. Okay, you can see here. Then this is the case of the starting winding. Then we'll move to the main winding. Okay. Here, the main winding. When we are giving a supply, single phase supply, some current flows through the main winding also. The main winding is highly inductive. What is the peculiarity of the purely inductive circuit? The voltage and current will be what? Voltage and current will be out of phase. The current lags the voltage by a 90 degree if it is a purely inductive circuit. Okay. But here it is not purely inductive circuit, but it is almost, it is a highly inductive circuit. So the current IM means current through the main winding. IM lags the voltage by a angle phi m, which is very, very much larger than phi s. Okay, these two currents are out of phase. That is, the angle between two currents are theta. So these two currents make a rotating field. Okay, instead of pulsating field, a rotating field is produced. Okay, thus when a rotating magnetic field is produced, what will happen? The rotor cuts the rotating and EMF is used in it. Okay. Is it clear? Okay, this is induction motor. I will explain it once more. You can see here two figures. First one is a simplified figure. Second one is a detailed figure. In the simplified figure, you can see a rotor here. This is the rotor part, and there are two windings. Here is the starting winding or the auxiliary winding. This is the centrifugal. This is the main winding, and this is the centrifugal switch. This figure is drawn in detail here. You can see the rotor part here is drawn here as represented here in detail, and the main winding is shown here. Okay, the starting winding is shown here. The peculiarity of winding is it is highly resistive, so a resistance is connected in series, and a centrifugal switch is also given. Centrifugal switch is closed. Okay, centrifugal switch is closed, so current flows through this circuit and also through this main winding. Hello.
Ma'am, we have received a few questions. Can I ask a few questions right away? The first question is how the field is made rotating in forward and backward direction.
Field cannot be rotated in forward and backward direction. That's what we are explaining, that single phase induction motor is not self-starting. Okay, if the field are resolved in two parts, two fields forward and backward, that is the double revolving theory. There will not occur any torque. The torque will not be produced. We are providing some other means to start the motor. Okay.
Okay. It was clear, ma'am. Another question is why we are using a centrifugal switch.
We are using a centrifugal switch to cut out the auxiliary circuit or auxiliary winding after. It is only needed during the starting. After that, it is not needed. That's why the centrifugal switch is used.
Okay, ma'am, that is clear. Another question is where do we require single phase induction motors? What are the applications of single phase induction motors?
Okay, induction. There are many applications in day-to-day lives actually. but it is mainly required three-phase supply. If we are not getting any three-phase supply, and at that the second is that if the AC is and the single phase induction motor is portable, so you can use in that type of applications also. Okay.
Okay, ma'am. I have another question. Why is power factor of a single phase induction motor low?
The low power factor of a single phase induction motor is mainly due to the large magnetic current, which ranges between 60% to 70% of the full load current. Okay.
Okay, ma'am, that was clear. I have another question regarding the switch itself. So why a centrifugal switch is named so?
Hello, ma'am. Hello.
Why?
Repeat
Yeah,
the
I will
question.
repeat the question. I will repeat the question. Why a centrifugal switch is named so? Is there any reason to name that switch as centrifugal?
There is not a particular reason for that. That's it. There is no particular reason for that.
Okay, ma'am. We can continue the session, ma'am. The next 20 minutes, we will be having another lecture, the continuation of this part. Then we will be answering the next questions in the last 10 minutes QA session. Thank you.
Okay. Okay.
Okay, ma'am, you can continue.
Discussing. Okay, we were discussing about the motor. Okay. There is a main winding and a starting winding. Main winding is highly inductive. Starting winding is highly resistive. So we'll get two currents or phase difference. Here we see the phasor diagram. The voltage V is drawn here, and the IES starting current is lagging the voltage by an angle phi s. I am lagging the voltage by phi m. The phase difference between IS and IM is theta, and because of this phase difference, a rotating magnetic field is produced. Okay, this magnetic field is actually weak than the three-phase induction motor, but after starting, it will it will get the magnetic field get strengthened. Okay. Next, this is the explanation for what we have here. This is the characteristics of split phase. First is the starting torque TST is 1.5 to 2 times full of the torque. Second characteristic says the starting current IST is 6 to 8 times full load current. Third is it is low cost machine, and it is most popular. Fourth is it can be used as a constant speed motors, and for moderate starting torque and starting periods are infrequent. Okay, example, to drive blowers, washing machine, burners, small machine tools, etc. We are using this kind of machine. Speed curve of the split phase induction motor. This is all as the three-phase induction motor. You can see the torque by using the starting winding. We made the torque high. This torque is here. I will show. Okay. The torque is high. Instead of 0, the torque is high because If we are not using any starting winding, the torque will be 0. We have explained it earlier. Here we are using a starting winding, so torque will be a large value. Initial torque will be there, and the starting period, and after that, when the motor at the synchronous speed, just to the running condition. That's what we are seeing here. Okay. Type of the induction motor, as its name implies, capacitor start induction motor means there's a capacitor to the starting instead of that resistance in the induction motor, we are providing a electrolytic capacitor here. Okay, here you can see this is the simplified simplified figure, and this is some more detailed figure. In this figure you can see this rotor, there is a main winding and a starting winding, and there is a centrifugal switch, a starting winding in series. Okay, the voltage V is applying to a single phase voltage V is applying to the machine. When a single phase, okay, we can move to this detailed figure. I will explain this. This is the rotor part. This is the main winding part. This is the auxiliary winding. Okay, this is the centrifugal switch. This is the capacitor. Okay, when we apply to this machine, current flows through the auxiliary winding. The auxiliary winding here, the is highly capacitive. Okay, whereas in that split phase induction motor, it was highly resistive. Here, this auxiliary winding is highly capacitive. So what will happen? The current leads voltage by an angle. If it is a purely capacitive circuit, the voltage, the current leads the voltage by 90 degree. But here we are using a highly capacitive circuit, so the current leads the voltage by an angle. Okay, then the main winding, the here the current through the main winding will lag the voltage by an angle. Okay, I'll show it in the diagram. This is the phase diagram. Okay, this is the voltage. This is the voltage part, and the IS, the starting current, the auxiliary current, that leads, since it is highly capacitive, that leads the voltage by an angle phi s. Okay, IM is the main current, and it lags the voltage. Okay, there will be a phase difference between, that is theta. It will be a there will be a phase difference. This phase difference will help to produce a rotating magnetic field. Okay. Next is the torque speed curve of the capacitor start. Here the is very high compared to the resistive, split phase induction motor or resistive start induction motor. The starting period is shown here, and it attains the 75 to 80% of the synchronous. It will switch to the running position or running operation. That is the figure shown in this torque slip curve. Okay. Next, capacitor run induction motor. Okay, capacitor start and capacitor run induction motor means there are two capacitors. See, even in there are two figures you can see here. This is the basic figure. This is the detailed figure. This you can see C1 and C2. It is marked as CR and CS here. Okay, there are two capacitors. The capacitor 2 or the C2 or CS is used during the starting time only, and after that it is cut out circuit. The C1 is the same principle of operation. Here it is the same as that of capacitor start and capacitor run capacitor start machine. This is the speed curve of the capacitor start, capacitor run. This is the starting period and this is the running period. Okay. The capacitor used as capacitor is very that is 10 to 15 times higher than CR. Okay. This type of motor provides better power factor, 0.8 to 0.95 as the power factor, and the cost will be high. Next is permanent capacitor single phase induction motor. A single capacitor is used. It is connected to the single phase, permanently connected to the winding. Okay. No centrifugal switch is provided here. This is the torque speed curve of the permanent capacitor single phase induction motor. Here you can see this is the rotor part. There is a main winding, there is a starting winding, and a capacitor. The capacitor is used to start the motor, because the capacitor leads the voltage, and this main winding is highly inductive that lags the voltage. There will be a great phase difference between the IS and IM, and that will lead to a rotating magnetic field. Next is shaded pole induction motor. Here you can see there's a rotor and the stators. These salient pole type stators. On the stator we are providing some here it forms a closed circuit and a current flows through it. Okay. When single phase supply is given to the stator part, three parts we can classify it into three operating parts. First one is when the current, input current, starts 0 to position, that is the current is increasing. Will happen a flux produced while current is increased through this windings. A flux is produced. This flux induces this flux current in shading area. Okay, This current, character of this induced current, it opposes the cause. Here, the flux is the cause, so it opposes the flux. The cause producing the increase in current is the flux, so it opposes the flux. That is shown in this. So, greater portion of the main flux passes through the unshaded part of the main flux, through the unshaded part. Okay. Next condition is the region of maximum current. That is, we are providing a single phase current, and that is a sinusoidal wave is given from 0 to maximum current. The operation current means then there is no rate of change of flux. So there will be no induced EMF in this shaded. What will be the output, or what will be the operation? The entire flux flows uniformly throughout the section. Okay. Next is the third, maximum to 0. From maximum to 0 is decreasing. Okay, current is decreasing means you can see here. Current is decreasing means current, or the direction of current is reversed as from the first portion. Okay, then what will happen? Decrease in current is opposed means flux, and most of the flux passes through the shaded portion instead of unshaded portion. This is the 3 times, or 3 parts of operation. Happen after the 3 parts, the flux across the pole phase, isn't it? The flux is shifted from one phase to another. What will happen? This will cause a rotating field that will cut the rotor conductor. Will be induced and a starting torque will be there. Okay. Thus the motor starts. Is it clear? This is the torque speed curve. Here. This is the application of shaded pole induction motor. It is used in commercial as domestic field. We are using it in washing machine, fans, blowers, refrigerators, grinders, centrifugal pumps, hair dryers, etc. That's the end of some of the questions from this modules. We can discuss these questions. First, performance of 3-phase induction motor with single-phase induction motor. We have already what is the specialty of the phase induction motor, and what is the specialty of the single-phase? We have discussed it in this session. Okay. Second question is principle of operation of induction generator. Induction generator were discussed in the last session. Principle of operation, we were discussing mechanical energy is converted to the electrical energy, and advantages and disadvantages is the third question. It also we have discussed in the previous class. Okay. Fourth question is explain the operation of induction generator under self-excited and line-excited. Yes, there were 2 types of induction generator, self-excited and line-excited, that were discussed in the last session clearly. Next, give the condition under which induction generator may fail to build up voltage. Yes, the motor should be should rotate the prime mover is given to the prime mover drives the induction motor with a speed higher than the synchronous speed. Fails to attain that synchronous speed, the voltage build-up will be. Then explain double revolving theory for operation of single phase induction motor. Here we have explained the double revolving theory, that is the pulsating magnetic field is resolved into two components which is equal in magnitude and opposite in direction. So no torque will be produced. That is the double revolving theory. Next question is, with the help of torque slip curve, explain why single phase induction motor is not inherently self-starting. We have when S equal to 1, N equal to 0, the torque will be 0 because forward torque forward field there will be a torque, and due to the backward will be a torque. At this time it will be equal and opposite, and so no torque will be developed. Next is explain the different method of starting of single phase induction motor. We have discussed it here itself. There are 5, that is a single phase induction motor. Start induction motor, capacitor start capacitor induction motor, permanent induction motor, then shaded five types we have discussed. And principle and torque speed curve of the shaded pole induction motor. These are some of the questions from the 6th model.
Okay, ma'am. I will ask you questions which has been raised by the students in the QA box. So the first question is, what is the necessity of two capacitors in capacitor-run induction motor, and in household fan there is only one capacitor visible?
Induction motor. It requires only one type of capacitor. In two capacitors to improve the power factor during the running condition also.
Okay, ma'am, that is clear. Another question is from Lesson Matthew. Why are resistance split phase induction motor most popular?
Okay, due to the induction motor are most popular in markets, and also they are used where moderate starting torque is required. Okay, and also where starting periods are infrequent. Okay.
Okay, ma'am, that was clear. Another question is from Aparna Ashok. She has asked why no centrifugal switch is used in permanent capacitor starter.
Okay. It is not used because it is enough. It is enough for the second running, and no need of no need of cutting out this section from the circuit. The capacitor used is not that much.
Okay, ma'am. Another question is what type of capacitors are used in capacitor start and capacitor run single phase induction motor? What type of capacitors are used in capacitor start and capacitor run single phase induction motor?
Okay, there are two types of capacitors. One is the starting capacitor, second is the running capacitor. The starting capacitor is the electrolytic type of capacitor. Another second one is the paper. Okay.
Okay, ma'am. We are reaching the last 5 minutes. Yes, ma'am. It was clear. We are reaching the last 5 minutes of the session. Ma'am, could you please conclude the session? Like, could you brief the entire session in the last 5 minutes?
Okay. There were mainly module. First one, synchronous induction generator. Third one, single-phase induction motor. The induction generator, the working principle of induction generator was induction motor could be run as an induction generator if it is driven with a prime mover with a speed higher than the synchronous. That is, we are providing a mechanical energy and output will be electrical energy. Second is the in the induction generator itself, there were two types of induction generator, that is self-excited and line grid connected. Self-excited or isolated type means the generator is not connected to the three-phase supply. Okay. The second thing is the line induction generator means the induction generator is connected to the grid. The reactive power is delivered from the grid by this induction generator, and the active power is delivered to the three-phase supply, and reactive power is received from the three-phase in order to magnetize. Then comes the synchronous induction motor. In synchronous induction motor, as its name implies, it acts as a synchronous motor and an induction motor. At the starting time, it acts as an induction motor, three-phase induction motor. During the running time, it acts and a rotating is produced. This rotating magnetic field cuts the rotor and starts to rotate. But at the same time, we are providing a DC excitation to the rotor, and alternating north and south pole is developed. This north or south pole get magnetically locked with the rotating field and rotate with the rotor. Rotate with the magnetic. Okay. That was synchronous induction motor. Third pole motor. In synchronous induction motor, the construction contains the stator and a rotor. The main parts are stator and a rotor. Rotor is same as that of a squirrel cage stator. Stator, we are providing a single phase supply instead of three-phase supply. Okay. Here, the motor is not self-starting because when we apply single phase current, a pulsating magnetic field is produced. This pulsating magnetic field, according to the double revolving theory, this pulsating magnetic field, okay, having same and opposite in direction. So this forward and backward field any net torque. Okay, that's why it is not self-static. We are providing some means to start the motor. That are there are 5 types of single phase induction motor. Capacitor run induction motor, permanent capacitor motor, then shaded pole induction motor. Okay, these are the 5 types of induction motors. We have discussed the types operation of each and every induction motor.